Hello, everyone. Thanks for joining us for another Silicon Labs product podcast. I'm Isaac Sanchez, and today we'll be discussing how to protect 24-volt digital outputs with our power and isolation team. Joining us today are Senior Product Manager Asa Kirby and Applications Engineer Travis Lenz to chat with us. Welcome, Asa and Travis.
Thank you.
Yeah, thanks, Isaac. It's always fun to hang out with you guys.
Asa and Travis are coming off a recent successful webinar on this very topic. I've linked to that in the info of this podcast. Please check it out when you get a chance. Let's go ahead and start with Asa. So I'm pretty familiar with digital logic levels, and most are pretty low. 24 volts to me is huge in comparison and seems pretty unique. Usually when I hear 24 volts, I think about industrial power supplies. So what type of devices are we talking about that use these 24 volt digital channels? And why do the channels need protection at all?
Yeah, it's a great question. 24 volts is pretty big, and most people do think about it in terms of the power supplies on these plant floors. But what we're really talking about is programmable logic controllers, or PLCs. These are basically little industrial computers, right? You can embed them into devices and machines on the plant floor. And because everything runs on 24 volts, it was pretty common for that to become the digital standard rather than one of those low voltage standards. So these PLCs, they'll have lots of inputs and outputs, and those can be digital or analog. They'll also usually be running some sort of a user-defined program. It's written in a lot of different languages. The whole point of the device, right, is to bring in an input, process it through the user program, produce an output. That output is going to affect some system, and then this is a closed loop control. So that then impacts the inputs, and you have a nice, tight closed loop control device. That's the automation aspect here. We're controlling to kind of get to some task. Now, your second part of this question is really good too. Like, why do we care about protecting them? And the reason for that is where they have to live. Plant floor is a nasty place. I mean, it is dirty. It's full of giant spikes of voltage coming from things like motors. You have equipment that is deployed for decades on end with technicians rolling through periodically, replacing and cutting wires. So these devices are constantly dealing with unknown sensors. People who have to design these devices have no idea what actuators actually get connected to the channels. I mean, they're literally screw terminals, just open to the world, and it's up to the installer to actually hook this thing up properly. So you get all kinds of noise inputs. You can get all kinds of unknown wiring scenarios, loads that are too large, too small, and this has to last for decades, 24/7 operation. So for all those reasons, when you design one of these, you end up having to make a really robust channel design, and you think a lot about protecting it from these unknowns.
I see. Well, thank you for the thorough response. So given that explanation, it sounds like the plant floor or wherever these are deployed can be dangerous places for a digital channel. So if you're designing a PLC, you really need to build a robust design capable of handling anything that's thrown at it. Can you summarize the key design challenges that any robust design would need to address?
Yeah, well, and it all comes back to what I said about, this nasty environment. All those challenges culminate in some key things you've got to do in the design. The first one is tolerating overloads. Because we don't know what's attached to the channel, it's very easy for that to be an overloaded actuator, right? It could be something too large, or you could just have somebody miswire it and attach your output to a dead short. 24 volts into ground can sink a ton of power and blow things up. Also, need to be able to drive inductive loads. A lot of the actuators that you're having to control are things like solenoids and valves, even motors, right? Like an inductive load inherently is going to have a negative kickback, and that kick, just like an overload, can destroy your channel. So you gotta tolerate it. You also have to be able to deal with high temperatures. We talk about the plant floor, but a lot of times these things are deployed outdoors. Call it an exterior plant floor. Think mining equipment or earth movers. They're basically the same thing as machines on your plant floor, but now they got to drive outside. Or even remote locations where you need to control like a pump or a valve, right? So for that reason, the design has to handle high temperatures, not just ambient. A lot of times the actuators they're driving are going to pump a ton of power dissipation into the chip, really bringing up the junction temperature. And at some point, you can damage the device. Then you also get into things associated with the input power. So up until now, I've been talking a lot about how, it's just some blank screw terminals in terms of what actuators you're connecting to. But it's also true that you have no idea what the power coming into the device is. So that could be a battery. That battery could be undersized. It could be an industrial power supply that starts to get wonky after a couple of years and it starts to brown out. That brown out can cause all kinds of damage to the downstream actuators. And again, the channel can basically destroy itself. And on top of all that, you've got to be able to handle transients, noise transients, right? So a lightning strike propagates through the system, can take out your channel through a voltage surge. A big motor kicks on somewhere else on the plant floor, and that surge can propagate through all these combined channels and burn out your channel. So those are the key challenges: tolerating an overload, safely driving inductive loads, dealing with these high temperatures, handling unreliable power, and then tolerating noise.
So it definitely sounds like building a robust design is certainly possible, but things will inevitably go wrong in the real world when these designs are actually deployed. So most of those protections you described would certainly keep people and equipment safe, but the PLC itself wouldn't operate normally. Isn't that a problem too?
That's a really good point. So even after you design all these channels to have all this, cutting edge protection, and you can make it such that the actuator and the channel are just as safe as could be, most of the protections that are deployed are the kind of thing that would at least turn off the channel, right? In order to protect itself, it will shut down into a safe state. But that means that the thing you're controlling is now not operating the way it's supposed to, right? And so you have abnormal behavior, even though nothing's broken. And that abnormal behavior can make the system, and remember, these things are usually a part of a control loop. It makes the control loop unstable. And so you can just as easily damage other equipment or even, hurt an operator or a technician when these protections kick in. And so the way this really usually gets handled is you can't just protect. You basically have to protect and report that there has been some sort of unknown fault. That's a diagnostic. So diagnostics end up being critical. You do protection, but you got to do diagnostics too, or else it's potentially worse than doing nothing. At least if you did nothing, the whole system would blow up and there'd be smoke everywhere. And that's a pretty good indicator that something's gone wrong. When you protect without a diagnostic, you potentially can allow a problem to go unnoticed. And one of my favorite examples of this was a machine I found called the Woodmiser 2000. It was this industrial sawmill. You could imagine this piece of equipment. It's very automated. It's got motors and conveyors and valves on it. If there's a specific, say solenoid that operates a guard over the blade, right? Maybe that blade guard is there to keep people from getting their arms sliced off. If that channel goes down, right, and that guard doesn't come down over the blade, you might protect the channel. But with that guard not down, without telling the overall control system of the failed channel, you've left an opening for somebody to get injured. And that's really what we want to prevent. We want to prevent downtime. We want to prevent bodily harm. So diagnostics turn out to be critical.
You definitely bring up a good point, and you've convinced me. So it's not only important to protect, but also to have some feedback to the controller to process or do something, maybe alert. I imagine like a loud bell or something, or a buzzer.
Or screeching sounds, whatever it takes.
So protecting industrial digital outputs is definitely critical, but it definitely seems like a lot of work to do it right. Does Silicon Labs happen to have any parts that could make this job easier?
Well, I'm glad you asked.
Me too.
We do. We happen to have this thing. It's called the Si834x. It's an isolated smart switch. And, especially in this space, these 24 output channels are often driven by a switch. So a smart switch is one that has the protections and the diagnostics. And ours is isolated, which is yet another type of protection. And this turns out to be useful for a lot of different things. So this 834, besides just being able to source a ton of power So we can do 24 volts at up to 700 milliamps continuously. It has extensive protection built into each channel. So we are able to detect an open circuit. We're able to detect short circuits or overloads, thermal over temperature per channel or per chip. We can determine whenever the supply is browning out or if it's actually dropped truly to a level that's unsafe. We also have a really innovative demagnetization clamp. That's the kick protection, right? That's one of the things you got to deal with. And we've even built a special feature into it that allows it to basically handle an overload for a short period of time. We call it our inrush current mode. That's really good for things like incandescent lamps, which are pretty common still to this day for indicators on the plant floor. You got to be able to hit them with a ton of current, but then once they heat up, they kind of settle down into an area that's safe. So we've spent a lot of time in this device developing a smart channel with all this protection, and we have more diagnostics than any other switch on the market. 8 unique switch diagnostics get channeled back to the controller. So you can have this rich feedback about how your channel's working, and you can really develop a good approach to these faults, improving safety, keeping downtime to a minimum. All that in a real small 9x9 DFN package really leads the market in terms of size and capability.
All right, I appreciate such a novel solution from Silicon Labs. Travis, as someone who has worked extensively with the Si834x, how does this device protect the output from environmentally harsh inductive loads?
Yeah, that's a good question, and I think that it bears a little bit of background on the techniques used to address the kickback from inductive loads, as Asa mentioned earlier. So inductors behave, their IV curve is V equals L di dt, meaning anytime you change current flow through an inductor, a voltage is induced across the inductor, which makes it look like a source instead of a load. And this creates a need for a clamping mechanism. And the clamping mechanism is anything that will limit that kickback voltage and provide a path for the inductor to discharge safely without destroying the output switch. So there's some common techniques that are used for clamping, and the most common ones are passive and active clamps. Passive clamps will typically comprise of a simple diode, which will clamp around 1 or 2 volts, but it discharges the inductor very slowly. Zener diodes will clamp around 16 or 17 volts and discharge much more quickly, but they dissipate a lot of power. Another technique you'll see is active clamping, which uses some form of MOSFET or other switch to discharge the inductor with a robust current path. Another technique that a lot of industrial I/O manufacturers use is clamping by avalanche breakdown. And avalanche breakdown effectively lets the inductor voltage fly up to the breakdown voltage threshold of the output switch. And the body diode then breaks down and conducts reverse current, which occurs at a high voltage. So high voltage and high current results in a lot of power dissipation, which can lead to a lot of heat generation and the need for a big package. So those are some of the techniques that are used in industry today.
All right, so Travis, that sounds like a lot of different options to take. Which approach did Silicon Labs end up taking with the Si834x?
The Si834x uses sort of a combination of clamping techniques in what we call a multi-voltage smart clamp. This is a clamp that dynamically adjusts between 2 volts, which is our low voltage clamp, and 17 volts, which is our high voltage clamp. The 2-volt clamp is generally used at the beginning of the discharge cycle when the inductor current is at its maximum. The reason we use a low voltage clamp in this scenario is to reduce the total power that's dissipated by the clamp during the initial phase of discharge. Reducing the current through the inductor during this period results in a quadratic reduction in energy total stored in the inductor. That allows us to save on the total heat dissipation during the final stage of the discharge cycle, in which we use the high voltage clamp. We switch to the high voltage clamp in order to rapidly discharge the remaining current in the inductor to ensure that the actuator which is oftentimes a relay or other similar armature, effectively releases or closes towards the end of the discharge cycle. So this multi-voltage smart clamp allows us to effectively discharge inductors of various sizes without generating a lot of heat, allowing us to include this in a small form factor package.
All right, thanks for that excellent explanation. Going back to the key design challenges Asa mentioned earlier in this podcast, the first thing he listed was tolerating an overload on the output. How does the Si834x handle this challenge?
Yeah, as with the clamp, I think it bears a little mention to talk about how other devices do this. Typically, you'll see devices increase their output impedance during heavy load conditions in order to limit current. And this drives the junction temperature really high. Once the junction temperature reaches a threshold, then the channel just shuts off entirely to self-protect. But once that junction temperature falls below the threshold, the channel turns back on and heats right back up to maximum junction temperature, cycling through this high temperature on and off cycle as long as the overload condition exists. The 834X actually uses a patented technology called power estimation, and it's a real-time power estimator that calculates the output voltage and current at all times to ensure that the load is within spec. If the power estimator determines the load is out of spec, such as in a short circuit scenario, then the output impedance is increased to limit the current. If after 150 microseconds, just a short pulse, the overload condition still exists, then the channel will shut off entirely and wait for 500 milliseconds before trying again. This technique drastically reduces the power consumption during an overload condition, and it prevents a lot of current from flowing into a faulty load. So this allows the 834X to handle short circuit conditions for an indefinite period of time.
All right. Well, I appreciate you taking the time to explain those key features, Travis. But before I let you go, how would you summarize the advantages of the Si834X?
The 834X provides a lot of features that can help in industrial I/O design. We talked about the multi-voltage smart clamp, which provides an efficient and robust clamping technique to protect your device against inductive loads. The real-time power estimation technique also protects the Si834X during overload conditions and provides reliable protection. We also have 4 channels in a small DFN32 package, so it's very compact with high channel density to help reduce board space and BOM. There's the advanced fault reporting system that Asa talked about, which gives actionable diagnostics to the operating system for rapid fault servicing. There's also parallel or SPI interface for different input requirements, and all of this is compliant with the IEC 61131 PLC standard.
All right. Well, that's all the time on our podcast today. Thank you, Asa and Travis, for speaking with us today. The Si834X Smart Switching PLC output, it definitely sounds like a great and novel solution for industrial outputs in general. So again, if you'd like to take a deeper dive with Asa and Travis on this topic, I'd encourage you to check out their webinar on protecting 24-volt digital outputs as a part of Silicon Labs' Power Hour webinar series on Wednesdays. You can find the registration link in the info of this podcast, and I look forward to you guys tuning in.